This is the most important concept first-time calculus students will learn. This is a Taylor series, which allows us to turn functions like exponentials and trig functions into a polynomial representation. The idea comes from an infinite series involving the product of the function's derivatives and a value centered at a point A. The longer the series, the more accurate our function gets, giving us a good representation and approximation for the original function. This is incredibly useful when calculating values like e to the power of 0.3 or sine of 4.5, but that's a story for another time. Today, I will introduce the idea of a Maclaurin series and how it helps us show the Euler identity. If you don't know how to find a Taylor series, that's okay. All I ask is that you have some understanding of complex numbers, factoring, and series notation. Okay, let's get started. So here we have the Maclaurin series for e to the x, cosine of x, and sine of x. And to be honest, we don't really have to know what the Maclaurin series is, except that it's here on the screen. But what we're going to do is use these series to find the Euler identity. So let's go ahead and start with e to the x. So here's the Maclaurin series for e to the x, and if you recall, I mentioned something about complex numbers, and this is where it's going to show up. Let's go ahead and introduce a I into our exponent here. So now we're going to go ahead and include an I for every value of x that we see in our series. And naturally, we want to simplify this. And before we continue, keep in mind that I is just equal to I squared is equal to -1, I cubed is equal to -I, and I to the fourth is going to equal to 1, and it will continue that pattern on and on. So then that means that e to the ix is now going to equal to 1 plus ix minus x squared over 2 factorial minus I x cubed over 3 factorial plus x to the fourth over 4 factorial, and that will continue that same process for every power there. Okay, perfect. And now what we're going to go ahead and do, you'll notice that we have a couple values that have i's and the others do not. So we're going to go ahead and separate those in terms of values that have the complex number and those that do not. So we have e to the ix equals 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial, and this will continue. And you're going to notice that these are all the even powers. Plus, and now we have ix minus ix to the third over 3 factorial plus ix to the fifth over 5 factorial minus ix to the seventh over 7 factorial, and this continues on and on. And once again, these are the odd exponents. As we continue, we still have the left-hand side. The stuff in the first parentheses is going to stay the same. And now we're going to go ahead and factor out an I from that second parenthesis. So we have x minus x cubed over 3 factorial minus x to the fifth over 5th. That should be a plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And we continue on and on. Now, I'm not sure if you recognize these series, but these were the Maclaurin series that I introduced in the very beginning. So if I scroll back up, let's start with the ones with the even powers. The ones with the even powers are the same values that we have for cosine of x, and the one with the odd powers are the same for the sine of x. So we're just going to go back and rewrite our series as e to the ix is equal to cosine of x plus I sine of x. That's pretty cool. And you'll notice that this is basically the Euler formula. But now let's go ahead and write and insert a pi in for our x. So we have cosine of pi plus I sine of pi. And we can evaluate e to the I pi is equal to cosine of pi is going to be -1 plus 0 because sine of pi is 0. And that's going to give us e to the I pi is equal to -1. And we could bring that -1 to the other side. So we have e to the I pi plus 1 is equal to 0. And this right here is the Euler formula. I remember my calculus teacher, Mr. Bolin, did this in class. And he said, Miguel, you do not want to miss this. And honestly, I'm so glad he told me because it is just incredible.